Hello everyone. In this video, we will learn how to compare the differences and similarities between an emission and absorption spectrum. 2. Describe and explain how a line spectrum of hydrogen atom is generated. First, we will discuss what a continuous spectrum is. I am positive that most of you have seen a rainbow before. A rainbow is an example of something called as continuous spectrum. When white light passes through a prism, the wave with shorter wavelength bends more than that of the longer wavelength. We know that the white light consists of 7 different colors with different wavelengths. If we arrange all these colors in the increasing order of its wavelengths, we get violet, indigo, blue, green, yellow, orange and red. The violet color with the shortest wavelength bends the most, followed by indigo and so on. So, when the light comes out of the prism, it appears as 7 different colors. When you project these colors onto a photographic plate or detector, we get the following pattern. Such a spectrum is called as a continuous spectrum, and it contains all the wavelengths of the visible light. We call this a continuous spectrum because each color merges into the next color without any break or missing wavelength. In nature, when we have sunlight and rainfall at the same time, the raindrops act like tiny prisms and generate the beautiful rainbows that we see. In the next slide, we will learn what a discontinuous spectrum means. As the name suggests, it is not a continuous spectrum, and it will have either missing wavelengths or only a few wavelengths. There are 2 types of discontinuous spectrums for atoms. 1. Emission spectrum, also known as line spectrum, and 2. Absorption spectrum. In the next slide, we will learn in detail what an emission spectrum of an atom is. If we take a sample of atoms of type X and either heat them or irradiate them, the atoms inside the sample absorb energy. The atoms that absorb energy are referred to as excited. These atoms have higher energy compared to the atoms that did not absorb energy. The energy state of the atom that did not absorb energy is usually referred to as ground state. For now, we don't know what is happening inside these atoms when they absorb energy. We will discuss this later in the course. These excited atoms are unstable and they give off excess energy that they absorbed in the form of electromagnetic radiation. If we pass this electromagnetic radiation coming out of the excited atoms through a prism, it will split the electromagnetic radiation into individual wavelengths as discussed before. And then we project the light that is coming out of the prism onto a photographic plate or detector. We see a set of discrete, bright lines on a dark background. This is called the emission or line spectrum of the atom X. To define it, emission spectrum is a series of discrete bright lines on a dark background as a result of light emitted by an excited atom. The bright lines on the emission spectrum corresponds to the wavelengths of the light emitted from the excited atoms. Note that when energy goes into the atoms, it can go in the form of heat or light. But when it comes out, it does so in the form of electromagnetic radiation or light. Another important thing to note here is that The emission or line spectrum of an atom is like a fingerprint. That is, each type of atom has its own unique line spectrum. Therefore, we can determine the identity of an unknown atom by recording its emission spectrum and comparing it with the spectrums of all the atoms to find a match. The study of this spectrum is referred to as spectroscopy. In the next slide, we will discuss about absorption spectrum. Absorption spectrum is the opposite of emission spectrum. We take a sample of atoms of type X and shine some light onto the sample. As discussed earlier, the atoms absorb light and get excited. However, the light absorbed is only of certain unique wavelengths that are characteristic of the type of the atom. The unabsorbed light comes out of the sample. If we pass this unabsorbed light coming out of the sample through a prism, it will split the light into individual wavelengths as discussed before. If we then project this light that is coming out of the prism onto a photographic plate or detector, we obtain a pattern in which we see a set of discrete dark lines on a bright background. This is called the absorption spectrum of the atom X. The dark lines on the absorption spectrum are the missing wavelengths from the white light and are absorbed by atom X. In the next slide, we will discuss the differences between absorption and emission spectrum. Here, I have the emission spectrum and absorption spectrum of a sodium atom right next to each other. What can you comment about these two? Pause the video here for a minute and think about it. The emission and absorption spectrum of an element are photographic negative to each other. Now, what does it really mean? Each of these lines on the spectrum represents a certain wavelength. For example, the bright line on the left is 589 nanometer. Since it is an electromagnetic radiation, we should be able to calculate its wavelength from the formula frequency times wavelength is equal to c. And then we should be able to calculate the energy of the photon represented by this frequency. We can use the formula E is equal to h nu. In the emission spectrum, this is the energy of the photon that is released by the excited atom. And in the absorption spectrum, this is the energy of the photon that is absorbed by the atom to get excited. We can say that the atom releases the same amount of energy that is absorbed. In the next slide, we will discuss the line spectrum of a hydrogen atom. If we take a sample of hydrogen gas and pass an electric discharge through the sample, the hydrogen molecules first break into hydrogen atoms. These hydrogen atoms absorb energy and get excited. These excited hydrogen atoms are unstable and emit radiation consisting of discrete energies. This radiation, when passed through a prism and printed on a photographic plate, gives bright lines on the dark background. This is the line spectrum of hydrogen. The line spectrum of hydrogen contains 4 lines. The first one at 410 nanometers, 434 nanometers, 486 nanometers, and 656 nanometers. The next question is, why the emission spectrum of hydrogen, or for that matter any other atom, shows discrete lines on a dark background. Why doesn't it show a continuous spectrum like the white light? In the next topic, we will learn how the discrete lines in the atomic spectrum of a hydrogen atom were used to determine its electronic structure.